So each small square is one tree. Each brick, larger block, I don't know what you want to call this. So each one of these would be how much? 10 trees. And then this big thing would be how many? And all these are you guys noticing all these are just times 10 times 10 times 10, right? So the whole diagram would represent 111. So looking at small squares now with books, this small square represents 10 books. So the next brick of squares would equal 100 each, right? You don't have this, Troy. This is just for all of us. And then the big one would be worth for a total of 1,210. Okay. So I'm just showing you, we can use these bricks to be different representations, right? So let's look. The small square is 1 million stars. What might be a nicer thing than writing 1 million? 10 to the 6. So an additional factor of 10 for this next brick would be 10 to the 7th. And the biggest one would be 10 to the... Are you guys seeing that? Just another times 10 is another factor of 10. Zeph? Yeah. Oh, this was supposed to be a 2, wasn't it? Yeah, thanks. Okay. So if each one's a million... So what do we have here? We have 6 millions. Let's write it all out. We have 2 10 millions, and we have 100 millions. Cool. Everything's just times 10, times 10, times 10. You catching that? So, let's take a look at the next one. Each small square now represents 0.1. So 0.1. What would the next up equal? 1. And then next up would equal? 10. So we have 12.1. I screwed something up in this last one. Where'd that 6 come from? Why'd I write a 6 there?
Wait, how'd you get a 6?
I don't know.
You said we're going to go with 6 million.
Oh. Anyway. It's a 1. I think it's because that something with that exponent must have made me think that. And the last one. I'm glad I looked back. Each small square is 10 to the 3rd. So... Oh, yeah.
Mrs. Chen would get so mad if you put units down.
Good.
Every time I got like minutes.
Anyway. So here we got 10 cubed. What's the next one? 10 cubed, what's next? What's next? 10 to the 4th. What's next? Okay, so I put these all together, right? I have one of these, which would be 1 with 5 zeros. I'm going to actually go to the smallest. I've got 1,000, so there's my 1,000, right? I've got 2 of the 10,000s, and I've got 1 of the 100,000. What do you notice about all these answers? Now that I fixed this one, that would. They'll have a 1, 2, 1, right? And what's the only difference then?
Where the decimal is.
Yeah, the fact where the decimal is also could be said the factors of 10. Right, Ivy? Check out A. Here's things I want to point out. I have 4 of these, and I have 2 of these. Can everybody go with that? So check it out. There's 4 and 2, 4 and 2, 4 and 2. Okay, everything has 4 and 2. But, look at my factors of 10. From this factor of 10 to this factor of 10, it increases by how many factors of 10? 1 factor of 10. So that immediately eliminates which letter? A. The small to big is 2 factors of 10. So A cannot match with A. So the answer for A is actually B or C. But what we have to do from there is a little different. If we picked B, that means each one of these is a 10 to the negative 2, right? And each one of these would then be a 10 to the negative 1. And the question asks, what would the small square be? Well, if you picked B, you'd have to say the small square is equal to what? 10 to the negative 3. 1 fewer factor of 10 than the bar. If you picked C, Each little one could be 10 to the negative 2, and each big one could be 10 to the negative 1. One additional factor of 10. If you're looking at C, if you had a big brick, it'd have to be what? 10 to... If you're looking at C, if you went big brick, an additional factor of 10, 0 or 1. Cool. So, try out number 2 on your own again. I'll give you a couple, after you saw that, I'll give you a minute or two for a number, or B. I guess it's not a number, it's letter B. Let's look at letter B. We're checking this out now. Who can tell me what they notice about our exponents for our tens, or factors of tens? That's a little different on this one. Sean, you notice something? What's the jump?
It goes up one factor of 10.
So negative 3 to negative 2?
No, it goes up 2. Oh yeah, it goes up 2.
So negative 3 to negative 1 is jumping up 2 factors of 10. What's the only picture that shows a jump up of 2 factors of 10? A. A goes from single to 3. So A would have to be, each one of these is a 10 to the negative 3. And the large one then would be each a 10 to the negative 1, right? There is our 4 10 to the negative 3s and our 2 10 to the negative 1s. The reason we can say it has to be that one is because our exponents jumped 2 factors of 10. From single brick to large. Okay? So looking at C. Again, let's look at our exponents. It jumped from a 10 to the first to 10 cubed. What does that one have to go to? A. Because each one of these little ones would be a 10 to the first. I jump up 2 to go 10 cubed for this. What's the missing bar? What would the missing bar be? Yeah, right? Positive 2. We're in positives here. Yeah, the bar, if we had the 10 bar, that'd be a 10 square. Okay. And the last one, what do you notice about the exponents? They increase by what? How many factors of 10? 1 factor of 10. So, we can either have this be a 10 squared and this be a 10 cubed, or we can have this be a 10 squared and this be a 10 cubed, and a little one here would just be 10 to the first. Are we feeling that? It's all just 10, 10, 10s. Okay? So what you're going to do is you're going to try one of these on your own next, and then for this, I'm going to add some directions for this second one. Okay? For the second one, it says select at least 2 powers. I want 1 positive exponent and 1 negative exponent to start with your little brick after when you get there. Let's check it out, guys. So, if each small square is 10 to the negative 4 here, what's each bar?
10 to the negative 3.
10 to the negative 3, and each big one would be 10 negative 2. So if we were going to write this out, though, as like a decimal, are we good to understand each one of these is 1 100, each one of these is 1 1000, and each one of these is 1 10,000? Okay. So that would then be 0.02 1 2 3 4 5 5 4. We have 4 thousandths, 4 10 thousandths, 5 thousandths, 2 hundredths. Okay. Now, this could be fun. Who can tell me one of their negative exponents they gave to the small bricks? We'll see if I can get all your exponents. Ivy, what'd you put? 10 to the negative 3? And then you'd have 10 to the negative 2 and 10 to the negative 1. And did you notice that it just shifted everything in your decimal 1 to the right? If we wrote that, this is a 10, this is 100, this is then 1,000. Okay? Who can give me one of the positives they used? What's one of the positives you used? Zeph? 10 to the 16th, 10 to the 17th, and 10 to the 18th. Right? I'm not going to write that out because we would have a lot of zeros. But again, same numbers represented by the bricks, but different numbers because different factors of 10. And it's kind of a cool way to show really big numbers and really little numbers. That's what we're going to kind of work with next real quick. Checking this out, here's what I'm going to tell you. You cannot write this number as I write it. Around the world, 14 billion pencils are made each year. What I would like you to do is rewrite that number 14 billion using factors of 10. One way you could rewrite this is 14 times 10 to the ninth. 14 times 10 times 10 to the ninth.
Wait, what about 14 to the 9th?
Well, 14 to the ninth would mean something different. That'd be 14 times 14 times 14 times 14. That'd be different, right? But that's a good question. Now, I prefer myself to write this. 1.4 times 10 to the 10th. Why are these the same number? Who can explain to me why they're the same number? Yeah, Ryan?
You're just taking the 10 away from the 14.
Yeah, I'm moving my decimal one more place, so I'd have to multiply by one more 10, right? Kind of like when we just switched our squares in the last portion, right? Oh, this one's going to be fun. The mass of a proton. I need you to rewrite this one using factors of 10. The mass of a proton is 1.000 ... I'm going to write. And then, yeah, this one's pretty fun. 167. There are 23 zeros. Not counting this one. Not counting that one. After the decimal.
Wait, 23.
So who's got one for us to try here? This one's tougher. Ivy, throw one out there.
Like the answer.
Yeah.
167 divided by 10 to the -23rd.
So, if there's 23 zeros, we'd get to the point right in front of the one with 23 moves. So we would need 3 more moves. So it has to be negative 26. So we don't say divide by. The negative exponent has us dividing by those 10s because it's throwing those 10s in the denominator. So if I had all these zeros, if there's 23 zeros, I would get to the decimal right here with 23 moves, right? So we could write 0.167 times 10 to the negative 23. That's one thing. Anybody write that one? 0.167 times 10 to the negative 23. That would work. Okay. If you went to 167, that would take 3 more moves to get to the end of the 7. So we'd have to divide by 10 3 more times. I personally, for this one, would write 1.67 to the negative 10 times 10 to the negative 24th. That's what I would write. The only reason I would write it like this is that's actually this thing called scientific notation that specifically would. Yeah. Yep. Okay. So again, what's happening here is when we're dividing by 10 over and over, I would move this decimal over 24 times here to get back to the original, right? We have to divide by 10 to get back to the original with those little numbers. Over here, we're multiplying by 10. That'd send our decimal moving to the right all those times. So I want you to make sure when you see that positive exponent, you're seeing times factors of 10s. When you're seeing the negative exponent, you're dividing by factors of 10s. There's fewer factors of 10. That's why we use the negative, yeah? All right. The population of Russia, there's roughly 144 million. So I need this with the 10s, with the 10s, please. All right, who's got one answer for me? For number 3, I'm going to work down here for number 3. Who's got one answer for me? Be wrong even. Maddie. Okay, that works. Who's got a different answer for me? Yeah.
Picking this up. 14.4 times 10 to the 7.
Yeah, we'd have to move it one more additional time since you scooched it one left. Yeah. What's what? We'll do one more. JP?
1.44 times 10 to the 8.
Yep, that's the one I would do. This is the scientific notation version. So all these are the same value, right? Because we're just manipulating factors of 10. Right? All right, last one. Diameter of a bacteria cell. I'll write this one out. 0.0000002 meters.
How many zeros?
Who's got one for me here? Sean.
10 to the -7 times 2.
2 times 10 to the -7. So 1, 2, 3, 4, 5, 6, 7. Yeah, I'd put it right there. Perfect. Who's got another answer? Anybody? Yeah. Olivia.
0.2 times 10 to the -6.
Yeah, so I would, let's check that out. 1, 2, 3, 4, 5, 6. There's an additional factor of 2 because it's one more larger where you put the decimal. Yeah. It needs to go one more spot. You could also do 20 times 10 to the negative 8 if you really wanted to.
Or you could do
200 times 10 to the negative 9, so on. These are all just manipulations of decimal places with factors of 10.
What's your
Big idea? To move the decimal to the right, we multiply by positive 10s. To move the decimal to the left, we multiply by negative powers of 10. Because negative powers of 10 are just dividing by 10. Okay? It's the inverse. And we already learned that the reciprocal is what a negative exponent means. It's all coming together.